I think we're recording. So if you want to say hi to all of your missing buds.
Hola. Nice to see you.
Okay. First period, guys. We're doing this for you, for your benefit.
Did we win? State playoff?
Here, let me.
Is the thing in Waco?
It is like state finals, right? Like
No, it's state playoffs.
Oh,
they're
so
in the
they have to go
semis.
through a whole
Yeah, they're in semis.
because everyone was saying, "Oh, we made it to the state."
Well, it's
Like not yet.
They're not even. No, they're not in the final.
Okay.
How many games do they have? Like two, three?
I think 2 maybe. Not
All right.
exactly sure.
We're going to finish 3-4. We're going to finish 3-4 this morning, and it concludes with this topic about what are known as inflection points. And an inflection point is a point on a graph where the concavity changes. Okay, so I've tried to draw this or illustrate this with these two figures here. So if you remember, concavity has to do with the idea of the second derivative, right? If
Can I get to check in with the first period before we go?
yeah, you gotta go check in.
With you or?
Oh, you just go, dude, go. Yeah.
That's what Mr. Clark told me.
Okay,
Or
okay.
Mr. Zeal told me to do.
Okay, all right. Zeal, yeah.
Bye.
Okay, see you, buddy. See you, buddy.
Yeah.
All right. All right. So inflection points are points where the concavity of the curve or the graph changes. Concavity has to do, remember, with the second derivative, and we talked a little bit about this last time, where concavity or where the second derivative is positive. All right, that means that the first derivatives are increasing, right? So the concavity is up. Here, just let's go back, take a look at that real quick. Okay, so in this case here, f is concave up, f prime is increasing, so f double prime is positive, all right? And then above that, we drew this situation here, where f double prime is negative. That means that the derivative is decreasing, all right? The derivatives are decreasing, the slopes of the tangents are decreasing, and that just means that f is concave down. And we don't have to get too abstract about the idea. Concavity just has the idea of a cave, something caved, okay? So either you're caved upward, all right, or you're caved downward. And that's the idea. But analytically, we want to focus then on the second derivative. So in these two pictures here, so notice what's happening to the derivatives there. What are the derivatives doing here? F primes are what? They're increasing, right? So they're negative, less negative, right? They're increasing. And so the second derivative then there will be positive. Okay? Here, all of a sudden at this point though, at this point here, the red point, the derivatives begin to do what? Yeah, the derivatives begin to sink back down. They get more negative there, so they're decreasing, right? And so here, the second derivative is going to be negative, okay? Same thing over here. I'll just use black here. First derivatives increasing, right? All of a sudden now, first derivative is decreasing, okay? So here we're going from f double prime being positive to f double prime being negative. Okay, so an inflection point is a point where the concavity changes. Analytically, that means that it's a point where the second derivative changes signs, okay? So
red dot.
Inflection point, yes, all right. An inflection point then is a point on the curve where second derivative changes sign. I'm not sure why I felt compelled to write it up in there, but okay. So we'll test an inflection point, just like we tested the critical points. Okay. By the way, we don't have a name for where f double prime is 0, all right? Or for that matter, undefined. So an inflection point can only occur where f double prime is 0 or undefined. Okay. But what we're looking for is a change in the second derivative. All right, a change in sign in the second derivative. We called these guys before, these c values, we called them critical values when we were looking for extrema. They, at least in Larson, they don't have a name. Okay.
So
Kids from Florida named them Boach points after a while, but yeah, we don't have to call them that. Yeah.
we're calling it.
Yeah.
They're no.
Wait, so are these just like essentially like the critical values?
These are like critical points in looking for inflection points. Yeah, these are like the critical values for your Remember, you didn't need to have, or not every critical value produced an extreme value. All right, so not every Boach point is going to produce an actual inflection
So
point.
are you like looking sort of for the extrema of? the
That's
first
correct.
derivative?
Yeah, that's very good. That's very good. That's correct. The inflection points are the extrema of the graph of the first derivative. That's true as well. That's a great point. But we're looking analytically here. We're looking for where this guy changes signs. You know, either plus minus on one side, or then minus plus on the other. We're just looking for a sign change. Okay. Okay. So you look at the exercises. Let me do 3. Are we on a normal Friday schedule? Okay. Okay, 8:15. All right, look at 27. Okay, so Dr. Larson wants you to find extrema and inflection points here. All right, he wants you to find both. So what do I do? Start taking the derivatives, that's right. Extrema, first derivative. Inflection points, second derivative, okay? Extrema, first derivative. Inflection points, second derivative. So let's start with the extrema. F prime.
So you have to use product.
Yeah, let's not, this is a third power. I don't want to foil that whole thing out, so let's just think product rule here. So F prime G, right, plus F, all right, what's a G prime here? Danielle, you want to give it a crack? What's the derivative of G, what's the derivative of this guy? What's G prime?
Don't you just
GDX.
take 3, put it up front, and then so 3x minus 12 to the second?
Well, 3x minus 4,
Oh, okay. To the
okay, to the second. All right, so that would, all right, that's the FDU, right?
Mm-hmm.
All right, what's U prime here? What's the du dx?
1.
1. Good. I just want to make sure that you're cool that you see that. Okay.
Yeah.
All right. Good. Okay. We want to. This is a polynomial equation, so we don't have to be concerned about where it's 0 or where it's undefined. But let's solve the equation equals 0 here. So type 2, what is the strategy on a type 2? I don't care what level of math you're in. What are you going to do on a type 2? You're going to create a zero product. And so how are you going to do that? How do you create a product in math? Factor. You factor. Yeah, that's yeah. Think about it. That is the premier skill that you learn in algebra, and you see it. It's just always with you. You know, even in the deeper realms of calculus. Okay. So what can we factor out there?
X minus 4 squared.
Yeah, the x minus 4 squared, right? This guy is common. X minus 4 is common twice to both these terms. So let's pull it out. X minus 4 squared. And what am I left with?
X minus 4.
Yeah, I've got 1x minus 4 there.
Plus 3x.
Good, plus 3x. Yeah, very good. Okay, all right. Remember, that is the strategy we use to solve type 2 equations. And then we invoke the zero product property, right? So we set each of these factors equal to 0. So either x minus 4 squared, right, is 0, or let's simplify this. What is this? 4x minus 4. Good. Okay. All right. So what kind of solutions am I looking at here? X equals 4. Good. 4 or 1. Good. Okay. Since Dr. Larson wants you to also find inflection points, then let's go ahead and we'll use the second derivative test. So let's wait to test these guys. We'll wait until we find the second derivative. All right. So second derivative. Let's use a simplified form of this first derivative. Okay. So let's revisit the first derivative. F prime is equal to right here x minus 4 squared times 4x minus 4. Okay.
Just plug it in.
Well, not yet. If we're going to do the second derivative test, Daniela, we'll take the second derivative. I just wanted to find a decent form of this guy before we took it. Okay. Okay. So what rule governs here? What differentiation rule? Differentiation rule. Yeah, product rule. Good. All right. So f double prime. Okay.
So
F prime.
is 2 times x minus 4 quantity.
Yeah, the udx again is 1, so 2x minus 4, f prime g, right, plus f x minus 4 squared. Good. G prime is just 4. Good, times 4. Okay, now, since we want to find inflection points, I know that we have these two critical values up here. By the way, let's just go back and call them CVs. Okay, critical values, just so we kind of don't lose sight of them there. We need to go back and test them and find those extreme values. But since we've got this second derivative like this, and we need to find inflection points anyway, let's go ahead and just keep working here, all right? So I'm going to set this guy equal to 0. And it's not undefined anywhere. So again, inflection points, like Brett mentioned, inflection points are the critical values of the first derivative function. Okay, so if we graph the first derivative, we'd be looking for its extrema values. The first derivative's extreme. Okay, so we're going to solve this zero equation here, and again, it's a type 2. So what's my strategy on a type 2? Yeah, to factor. What can I pull out there?
X minus 4 and 2.
Yeah, good. So 2x minus 4 is common to both. And what's left?
4x minus 4.
Yeah, 4x minus 4.
Plus x minus 4 times 2.
Plus
2x minus 4.
Plus, we've got an x minus 4, right, left there, and a 2. So plus 2x minus 4.
It's 2x.
Well, there's a 2 left from this 4,
Right.
and you left then an x minus 4, 1 x minus 4 there. Yeah. Okay. I told, I had our, that half day we all met as a math department, and I told Mrs. Whitson how much she appreciated her.
Oh.
You said that day. She really appreciated that. Hey, listen, seriously, teachers, especially elementary, I think, and middle school teachers, they really appreciate when you guys say good stuff about them, because they kind of get left, once that you leave those classrooms, it's rare that, they come back, you come back and, they get to know how well you've done and how much they poured into you, that's been good. But anyway, so she appreciated that. All right, so equals 0. Okay, so tell me about that equation.
You can drop a 2.
Yeah, so, we can just throw this guy out. That's right. He can just go. Right, is that okay? He's a constant factor here. You can just divide him off. So either x minus 4 is 0, or, let's see if we can tidy this thing up again. So 4x and 2x, that's 6x. Negative 8 and negative 4. All right, that's negative 12.
Because you took the 2. Oh, wait, never mind.
Okay?
Yeah.
Okay, so this is kind of unusual. What happens here? X equals 4, right? Turns out to be a potential place where the second derivative changes signs.
And 2.
And x equals 2, yeah. 4 or 2.
So those are the inflection.
Well, we don't know yet. We have to make sure that the second derivative is going to change signs there.
But they're the potential.
They're the Boch points, yeah.
Yeah.
They're the Boch points. Yeah. So we will look at that in just a moment here. Well, in fact, I'll tell you what. Let's do this. Let's go ahead and find a clean version of the second derivative, okay? Because we're going to need that clean version not only to do the test on the Boch points, but also to test the critical values to see what they are above. So f double prime. Let's get a clean version of this. So, are you guys okay? We can throw out this 2 completely. A positive constant factor will not do anything to the sign of a function at a point. It's just how positive constant factors are. They don't do anything. A negative would. A negative would change the sign, but not a positive. So that guy doesn't matter for us. So because I'm not really interested in the actual exact value, all right, of the second derivative. So I'm gonna toss him, and I just want this part here, x minus 4. Okay, and then what was that? 6x minus 12.
Mm-hmm.
Well, what's interesting here? Look at this. If we pulled a 6 out of here. Okay, x minus 2, we can toss the 6 as well. So really, this is not really equal. Here, to be fair to you, because I think that the people listening to this later, if anyone listens to this, they might not like this. So let's do this. All right, see that 2 there? See that guy? And see that 6? They're both factors. So we'll go ahead and just join them and call it a 12. The 12 is not going to do anything. The 12 is not going to do anything there, okay? It's not going to do anything to the information. It's not going to skew the information that we need, okay? we're not interested in the actual value of the second derivative, all right? We're not doing an acceleration problem, and we're not in Hans' class, and he's asking you for the acceleration at a certain, value of displacement. We just want to know the sign of the second derivative at the points. So, all right, let's go back then and do the second derivative test. What were our critical values?
4 and 1.
Okay, good, 4 and 1. All right, so CVs.
So that's the critical value. You have to check the critical values first.
We don't have to, good question. We don't have to do the critical values first. These are two separate sets of points.
Mm-hmm.
This is for the extrema.
Okay.
Right, 4 and 1. And so he just wants you to see whether or not these guys are, extreme values. And so by the second derivative test, well, what happens at 4? No, what happens at 4?
Well, it's 0.
Yeah, so what, memory from yesterday?
Good morning, students and teachers. Please pardon this interruption. Any students who have received permission from their parent is on Ms. Westmoreland's list to be released at 8:30. Please do so at this time. Any student who received permission from their parent is on Ms. Westmoreland's list to leave for the volleyball game at 8:30. Please dismiss at this time.
Okay, so that guy. So what did we say yesterday in class when the second derivative gave a 0 we didn't. Yeah, these are critical values. When the second derivative gave a 0, what did we say?
It was
Yeah, not undefined, but the test failed. Remember?
okay.
All right, so test fails. I don't like how I spell fails.
So does that in any way, shape, or form affect the inflection points?
Okay, that's a great question, and the answer is no, not at all. Inflection and extreme are just different sets of points. It's just a different feature of the graph that you're examining. Okay. Okay, so let's do this. Well, we can tell what happens at 1, though, right? What about at 1 by the second derivative test? So negative, so positive, right?
Yeah, positive.
I shouldn't have put equal sign. Well, and remember, Daniela, all we really care about is whether it's positive or negative.
Right.
So if it's positive, then what's happening at 1? If it's positive, that means what? The first derivatives are doing what? They're increasing, so you're passing through a min. Yeah, you're passing through a realm min. So therefore, 1. Okay, let's go back and see what the y value is there.
So that's when you plug 1 back into the
Original, yeah.
The very original.
Right. So 1 gives you what? -3 cubed, so -27. Right. All right. So 1 -27 is a realm min. All right. Now what about 4 though? What are we going to do there?
Don't you not do anything because the test failed?
Well, the test fails. Then we're in a sense stuck at the beginning. We're stuck at how are we going to determine what it does there. I go back then, Daniela, to the first derivative test.
Okay.
So I need the first derivative, so let's go find a nice form of that guy. Okay, right here, see that guy? Let's take that guy.
And
X
plug 4 in.
X
there.
minus 4 squared, 4x minus 4. All right. X minus 4 squared, 4x minus 4. All right, so first derivative. X minus 4.
Isn't it?
Is that right?
Also,
Well, for the first derivative test, though, we don't plug it directly in. We know that the critical value is going to make that 0. We have to test each side of it, okay, for the first derivative test. The 4 we could have dumped, but it's fine. He's here. It's totally fine. So, all right, so go like this. 4. Okay. So let's check left and right of 4. This is the first derivative test. All right, so pick something left of 4.
3.
Okay? No matter what you choose here, what's going to be true?
It's gonna be positive
Why?
because it's square.
Because it's squared. So this guy's always positive. This guy's always positive. If you pick 3 here, all right, 4 times 3 is 12, right? Minus 4. Okay. Yeah, it's positive. Okay. Okay, sorry. All right, pick something bigger. What's going to happen? Still positive. All right. So what can you conclude there?
They're both positive.
Well, yeah. Okay. So what can you conclude from the test?
That it's a maximum.
There's no extreme.
No extrema. Remember that in the first derivative, what's happening here? Yeah, what's happening here is at 4, you have some kind of situation like this, where the derivatives left are positive, right? Right at 4, there's 0. Okay, but then after 4, they continue to be what? Positive. Okay, so you'd have no extrema. So at 4, we don't get an extrema. All right, so no extrema produced at 4. No extreme.
So if there was an extrema, what would it look like? Like
For the
negative,
first derivative test,
positive?
there has to be a change in sign. There
Okay.
has to be a change in sign in the derivative.
And then from there you could.
Yeah, if it went positive to negative, then you know you had a max.
Oh, okay.
If it
was
went
negative
negative to positive, you know I had a min. Yeah. It's amazing what we can do with these ideas. Absolutely amazing. All right, to the glory of the majesty of the king. Okay, so this ends our search for extrema right there, that realm in.
Right.
Okay. The last thing we needed to do here though was to test those inflection points. So let's go back and where were our inflection guys? Or the Boche points. Okay, Boche points were 4 and 2.
Mm-hmm.
All right, so we want to test those.
And we test those with.
Set in the second derivative.
So
Alright.
that's the x minus 4, x minus 2.
I don't even, yeah, it might be. I have to, we'll go back and look for a minute. I don't even remember what. Now let's test the Boche points.
So this is where you test for inflection points.
That's correct, yeah. So we need to go get a form of the second derivative. And like I said, I think, I hate putting equals next to something that's not equal. So that, right here, Danielle, we'll just use this guy, right? 12, x minus 4, x minus 2, yeah. The
But
12
you
is
disregard
not,
the 12.
yeah, exactly. He's not going to do anything for this analysis.
So we've already tried 4 with the second derivative.
Yeah.
What's that?
We already, because 4 was a.
Well, the first, but the first derivative test just tests it for its extreme character, if it's extreme or not. It doesn't.
Well, we also tested with the second derivative test first, and it failed at 4.
Yeah,
That's why we
because
went back
it
to
was
the first
0.
derivative test.
Yeah, but wait a minute. No. Listen very carefully. The first derivative test, though, the second derivative test is also a test for extrema. Okay, that's something to impress.
Oh, but this is a complete.
The second derivative test. Listen, both the first derivative test and the second derivative test are extrema tests. Okay, they're not inflection point tests. Okay, they're not inflection point tests.
So what are we testing for?
We're testing to see if concavity changes here. Okay, we're testing to see if concavity changes. So at, what were the Boche points? 4 and 2. All right, Boche points 4 and 2. Okay. All right, so 2, 4. Now remember, we're testing to see whether or not the second derivative changes signs. This is an inflection point test. It's not doesn't have a name, to be honest with you. They don't call it anything. Larson doesn't call it the inflection point test or anything. You're just looking to see whether or not the second derivative is going to change signs.
So in this case, we do the same thing we did with the first derivative, where we pick a number.
Yeah, it's like the first. Yeah, to be fair, it's really, and Brett said it earlier. It's really the first derivative test applied to inflection points, because inflection points are extrema points for the first derivative function.
Yeah.
All right, so, so tell me what happened here. Okay, so left of 2, pick something over here.
1,
All right, 1, so negative,
3,
negative,
yeah, positive.
positive. All right, pick something in here. 3, all right, positive, negative, negative. And how about over here?
Positive.
Yeah, it's positive again. Okay, so the second derivative does change signs.
Right,
So what can we conclude?
It's
that there is.
This is an inflection point
there
test.
is a
This is for inflection point test. It means that
they
at
are-
x equals 2, we get a concavity change.
Right.
And at 4, we get a concavity change, okay? So these are inflection points. So let me go back and get the values of these guys. So 2, and what's the function value of 2?
Oh, are you taking these and going up to
Yeah, just to get the actual
the
value.
beginning again?
So negative 2 cubed is negative 8 times, okay, so negative 16, and then 4 is 0, right? So negative 16. All right, so 2, yeah, yeah, good call. All right, so 2, negative 16, and 4, 0. R. Inflection. Alright. I.e. points on the curve where the concavity changes.
So if it just asks for the inflection points, you really don't have to do anything with the critical values, correct?
Correct. Critical values and inflection points, they're really just two separate sets of values. In fact, I don't think they can even be the same.
So is there something
Unless
that we
it's
could?
I'd have to think about that. I don't think,
So like, you said there's no name for testing for inflection points. Is there something should we just like refer to it as the inflection point test?
you can if it'll help you.
Just because like I want to be able to distinguish it in my head.
Yeah.
Think about it.
Yeah,
I
if
wanna
you-
be
when
able to
you're-
call it something.
When you're looking for sign changes of the second derivative, that's what you're doing. You're applying the inflection point test. There's only one. We don't, and you could, listen, to be fair, you could take this a step further and say, well, we could find the third derivative and then have a third derivative test on the inflection points. But no one does that. No one does that. We don't do that. We stop. Remember what I told you? We stop at the second derivative. Okay, that's it. Done. Okay, I got. Yeah, that's fine. I just want to do now a couple exercises in the think about it kind of category. I'm going to give you some problems to do from this part, but just for the sake of time, I don't want to keep going there. Let's look at. Let's start at 40. Let's do 43. Okay, so I'm going to sketch the graph that he gives you in 43. Okay, something like that. And Dr. Larson wants you to sketch the graph of f prime and f double prime. F prime and f double prime. All right, listen very carefully. The key to the sketches of higher order or derivatives or higher order derivatives is to first plot where the zeros of those derivatives would be. In other words, understand what's happening at the extreme value of the function. So in other words here, the first derivative here at 0 is going to be 0, right? Because the tangent line is 0 there. So I'm going to plot that point, okay? Also notice that the first derivative here is going to be 0, right here, okay? Halfway between 1 and 2, so I'm going to make that 0. All right? The first derivative is positive, right? Positive, 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 until we hit this point, okay? Then it's negative, 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 negative until we hit this point, okay? So this guy would look something like this. I don't like it. Sorry. Okay? Something like that. All right? Now, where does, I don't even like that. Let me try to make it a little bit more parabola-like, which it is. Okay. Now, so F, the red graph is F prime, the black graph is F. All right, what about F double prime? What would F double prime look like? Well, again, what we want to do is we want to go to the red graph and identify the extreme values there, okay? So the derivative of this graph is going to be 0 here, right, where the tangent line is 0, okay? By the way, what does that correspond to? What does this C value correspond to? Where you, and Brett said this earlier, where we have an extrema, or an extreme value in the derivative, that would correspond to what? Inflection point in the original graph. That's exactly right. In other words, that's the place where the concavity changes. That's exactly correct. Yeah. Okay? Think about this just for a minute. Okay? Look at the black graph. Derivatives less. There, right there, they begin to increase. Okay? Look at what the derivative value is doing. Less. Right there, they begin to go and increase again. It's really cool, actually. Very cool how that works. Okay, so that's a 0, and that's the only 0. And so we go from what? From slopes values negative, negative. Here's 0, positive. So you're looking at this guy. Okay. So the blue graph is F double prime. All right? And that point right there is an inflection point. That is cool. Look at, okay, I've got just a few minutes, so we always end up like this. I'm going to start 51. And I won't finish it, I'm quite sure. And then later I'll finish it and put it in the notes. I'll give you, and I don't know what the homework is exactly yet. I'm going to give you some problems from 22 through 36. I'll give you a few from there, and then a couple from over here, including one of my favorite problems, 54. That's one of my favorite problems. I like it a lot. So I'll give you that, but I'll figure that out later. All right, so let's do 51, and we will call it a day. Starting here. All right, he wants you to find the coefficients of this function. It's a cubic, ax cubed plus bx squared plus cx plus d. By the way, this is, in my opinion, this is a very AP-like question, okay? He wants you to find the coefficients that satisfy these indicated conditions. So he wants a rel max at 3,3, rel max at 3,3. He wants a rel min at 5,1. And he wants an inflection point at 4,2. Okay. Remember, we say this all the time, and I know you might laugh when I say it, but it is so true. Math is all about relationships, okay? Because life is all about relationships, and that's because God is all about relationship. And so what you're looking for is how is what I'm looking for, how are the values of these coefficients, A, B, C, and D, how are they related to these specific requirements? What's the relationship there? There's a relationship. Remember, we're in calculus, when in doubt. Take the derivatives, yeah. Okay, so I know that if I want a max, right, at 3,3 or a min at 5,1, that means the derivative of that guy has to be 0 at x equals 3 and x equals 5, right? Okay, I will finish this and put it up. This is a good problem, though. This is very AP-like, all right?
Where is Mrs. Dew's room?
She's out in the deck somewhere. I think it's the first. I think it's the first walkway. Okay. Again, this part though will not be recorded. So, dear sweet people listening, we're going to stop the recording here, and I'll finish the notes though and put them up on mine. Yeah.
What, are you staying here after 4 of them? Are you done?